Yeah, hello and welcome to my gear webinar. My name is Tom Krause and I'm the head of the additive manufacturing at igus. And yeah, welcome to this online seminar, which is about 3D printed polymer gears by igus, save development time through online lifetime calculation. You will get the presentation afterwards, and afterwards we also have some time for your questions. So why producing gears by laser sintering or 3D printing? Basically, we have two different cases where we are printing the gears. The one is for spare parts. So if you have a broken car or machine and you need to have a gear which is not longer available. Here, for example, we had a case where a customer had a Stanley 750B from 1924, so really old car in this case. And yeah, this part was broken. It was used in the tachometer shaft, or it is the tachometer shaft. And yeah, the customer had the issue that he didn't get it anymore, and the part used in his car was worn out. And then, yeah, he drew it by himself. He measured the original part. He made a CAD drawing, put it in our online print service, ordered it directly, did also several tests, did also several changes, and now his car is running again. The other case is serious applications where we have a lifetime cost and time advantages with 3D printed gears compared to regular gears. For example, in this case, it was a gear with the inner square, so similar to a gear in this shape. It was just a bit smaller, more like this one, with a diameter of 26 millimeters, a width of 6 millimeters. And the customer needed here 3,000 pieces per year. And yeah, by mechanical production, the price was about €5.40 because of the inner square, because this is much more complicated to machine than just a regular hole. But by laser sintering or by 3D printing, we don't care a lot how the part is shaped. We care more about how many parts are fitting into the print room or how many parts we can make per hour, and not so much how the part is shaped by itself. Yeah, in this case, we had a big price advantage here. And furthermore, we had a lifetime advantage with the 3D printed gears. So a classical cost down, life up example, which we have here with 3D printing. But another big advantage at 3D printing gears is we can print more or less any gear in any shape. It can be, yeah, a regular toothing gear. It can be a worn gear like this one, or any other weird shape of gear. That's a big advantage. We don't need to think about how we can make it. We only need to take care of the minimum wall thicknesses, which is about 0.7 millimeters, and that the gear, of course, fits into the print room. And since the minimum wall thickness is about 0.7 millimeters, that's also the smallest gear module we can do here. So it's also 0.7. And besides that, we can really print any gear in any shape. That's the big advantage here. Another big advantage is that we can improve lifetime by optimizing the 3D model, because yeah, as I'm saying, it doesn't make much difference for us. Here, for example, you see two different worm gears. The left one is a worm gear which is made for mechanical production, so by milling, for example. The gear shape is simplified in order to make it more easy or more cost-effective to produce. But this is causing only a small contact area between the worm shaft and the worm wheel, which is causing a high load and a high wear. And yeah, at the 3D printing gear, I can optimize the gear shape because I'm not bound to any toolings here. So I can increase the lifetime by optimizing the shape, for example, in this case, by reducing the surface pressure. And I can have a much better lifetime at the same cost than with a not improved model in this case. This is another big advantage what we have here, and why we are already printing about, I think last year, about 40,000 gears already because of these advantages here. But why are we printing the gears at igus, or why are we making the gears? The big difference to all other 3D printing companies is our 3D printing materials, but also our regular materials, having always solid lubricants inside. So it's a mixture of different additives in order to increase the wear resistance up to 50 times. And yeah, this makes it possible to 3D print all kinds of special wear parts like gears, bearings, lead screw nuts, or any other part where wear and friction matters. And here you see an example how this performs in a test of an example of a bearing. The left one is a regular printing material. It is PA12 by laser sintering. And the right one is our Iglidor i3 with the solid lubricants. And yeah, it was about 20 millimeters in diameter and length, and there was 800 kilograms on load on it. And yeah, you see the regular printing material fails very quick. It failed totally. And at the iGlide i3 material, we have only a very little wear here. And that is the big difference we have at with our 3D printing materials from igus. So if I put it more in numbers, this is the test. As I'm saying, it's a 20 millimeter bearing pressed in a housing, and there's a shaft running in it. And I can put a load on it up to 1,800 kilograms. So it's more like a bigger car. You can put as load on such a 20 millimeter bearing, and you still have a similar wear rate compared to injection molded bearings. Yeah, you see Iglidor W300 is an injection molding material and has a wear rate of 25. The lower is better here. And Iglidor i3 is with 46, very close to the injection molded bearing. And yeah, you see the printing materials like ABS or PA12, the regular printing materials, have a much higher wear rate, so they are wearing down much quicker. That's the big difference, not only for bearings, also for the gears here. And yeah, which methods, 3D printing methods are we using here? Since at igus we're doing always motion plastics, we're only using, of course, 3D printing methods where we're using plastics. And here we're also only using methods with real plastics, not with some photopolymers where the properties change very quick over time. And that's why we're using these two methods. The first one is laser sintering. Here we have a powder. You see it in picture, and the powder is melted by a laser, layer by layer. The layer is 0.1 millimeter thick, and when the layer is lasered, then it moves down by 0.1 millimeters, and then the next layer of powder is spread out, and then the next layer is lasered again. And that's how we made by laser sintering about 120,000 wear parts in total, only here in Germany. And yeah, that's one method. And the other method is the filament printing, which is probably more known to lots of the visitors here. So this is the typical filament, which is pushed out at the nozzle. The nozzle moves in all three dimensions, and that's how the part is built. This is more suited for printing parts by yourself, because yeah, the printer is much cheaper, but also the price and strength and precision is not as good as at laser sintering. That's why we are using laser sintering mainly as a print service, and filament is mainly by customers used which are printing by themselves. And yeah, here we are having some lifetime tests, for example, for such worm gears with our iGlide i6, which is especially made for such gears. And here we have, yeah, in this test it was a gear similar to this size with 12 cycles per minute and a load of 5 Newton meters. And yeah, we needed to test here about a month. And after a month, we still didn't had much wear at the printed iGlide i6 gear, and the regular machined gear out of POM, for example, failed already after 620,000 cycles. So you see, we can even reach a higher lifetime than with regular machined gears. And yeah, that's another test result we did for such regular gears. Yeah, so yeah, as you know them from regular gearboxes. And in this test, you see a big difference from the different printing methods. So the FDM filament printing gears are holding not as long as the laser sintering gears, as for example Iglidor i3, which had the highest lifetime at such regular gears. That's why we're using also Iglidor i3 for such regular gears all the time. And you see we even have here also a 2 times better lifetime compared to regular POM milled gear here. And that's another big advantage you have here, that you can even reach a higher lifetime than compared with yeah, regular machined gears. Yeah, but yeah, at the end, you also want to have the lifetime in your application. You want to have a feeling for the lifetime for your application, maybe before you even start thinking about or even start modeling a gear. And that's why we made this free lifetime calculator for 3D printed gears. It's online, it's free, and you don't need to have any login. And yeah, I'm switching directly to it so that you can that I can show it to you. I hope it's now visible to the screen, the website. And yeah, it's very easy. You just put in your application data. So the number of teeth, let's say I have yeah, 30 teeth at the smaller gear. Yeah, it's really just the number of teeth. Then the width of the gear or of the teeth, let's say 10 millimeters. And then the modulus. The modulus is a value for the size of the teeth. Let's say 1 millimeter. And then you also need to put in these numbers for the second gear, because you're always calculating a pair of gears and not a singular gear. Let's say we have 60 teeth and also 10 millimeter width. And now you put in your application data, like number of revolutions. Let's say one. Oh, that was the wrong value. Let's say we have 100 cycles per minute and 1 Newton meter of torque. And at the end, you can put in some more informations, like is it running all the time, or is it running only 20% of the time? Do you have shocks, or do you have really strong shocks in the application? What's the application temperature, and what's the safety factor? So if you know your loads and speeds very well, you can choose a lower safety factor like 1.2, which is 20% safety. If you don't know your application so well, like loads and speed, then you choose a higher safety factor in order to be more sure about it, that it holds really in your application. Yeah, and then you get immediately a lifetime for the small or for both gears in this case. And yeah, then you have really quick a feeling for the lifetime of your application with these 3 printed gears. But let's say we have now a more, a stronger application. I'm increasing the torque from 1 to 2 Newton meters, and no change so far. I'm explaining later why. Okay, so at 3 Newton meters, we see already a big change here. The lifetime is a lot reduced, and if I'm increasing to 4 Newton meters, you see it's really a really low lifetime in hours in this case. And yeah, let's say you have such a case, then it's not done by saying, okay, it's not working. I can look into something else, because now it's the point where you have where you can play with the gear lifetime calculator, how you need to change the gear so that it holds for your application. Because now you can start changing the values here on the top, like the tooth module. Yeah, module is for the size. If I'm increasing to like 1.5, then again I have a really high lifetime. But if I'm increasing the modulus by factor 2, the gear also gets bigger by factor 2. You not always have this space. So maybe you start by increasing the width, which doesn't make such a big difference. Let's say from 10 to 15 millimeters. And then, yeah, we also have again a much higher lifetime here. And you see that's you can not only use the tool to figure out the lifetime for your application, you can also use the tool to check what do I need to change to have a good lifetime for your application. Of course, if you have, for example, one of both gears already, you have it already out of plastic or out of metal, then you can also choose the other material here for calculating at least the lifetime of the Equilibrium material. And yeah, that's how you can use it. Before I'm going to the next step, I want to explain some special cases here. For example, let's say you don't have 2 regular gears. Let's say you have a gear rack and a gear. So we are improving the lifetime calculation tool about that. That's also added. Until then, you can just calculate the rack like a big gear. Doesn't make a big difference at the lifetime, yeah. So you just take a gear with a really high number of teeth. Let's say number 90 or 100 teeth, and then it doesn't make a big difference at the lifetime if it's at a rack or a gear with 100 teeth. Another specialty is if you don't have gears rotating all the time. So if you have gears which are switching the direction of the rotation. This is of course a much stronger case because we have much higher loads compared to applications which are running all the time in the same direction. And in this case, you just take in the mode of operation strong shocks, and then you have a better feeling for the lifetime in your application. Okay, so last question: why is the lifetime limited to a certain number of hours? We had it here. That's based on the test results we made. So there's a maximum number of cycles which is tested so far for a lifetime. That's why there's a certain point where you don't get any more lifetime. It doesn't mean that you get more lifetime in your application. It only means that the tool cannot calculate a longer lifetime, which is in this case already a really long lifetime. Okay, so I'm switching back to my presentation. Again, I'm happy to answer your questions afterwards. And here again are the special cases which I already explained to you. But the most difficult part at this lifetime calculation is getting the input data. So the gear width, number of teeth and modulus shouldn't be that hard, because usually you have a feeling for it, or you just check it in the lifetime calculator to get good values. But what is more difficult is the load data of the gear, like speed and torque. Speed is also relatively easy measured, but torque is more complicated to get. And that's why I'm showing you how you can calculate the torque which is on your gear in your application. Basically, you can calculate it from two different directions. You can calculate it really from the application side. So you're calculating what's the load and everything, and then you're calculating back to the load on the gear. This is much more difficult. More easy it is to go from the motor. So what power does the motor have, and what torque, and then calculating to the gear. This is much easier. But please pay attention if you have a much if your gear or motor is much bigger than it needed to be, then you will calculate with much higher torques than you really have in your application. So in this case, you could reduce the power of the motor always a bit in order to find out the spot where it's not moving anymore, and this is regular more the load in your application. Okay, so let's say you have a stepper motor, and with a stepper motor it's a bit more complicated, because the torque on the stepper motor depends on the number of revolutions and the current which is set for the stepper motor. You just get the data sheet from the stepper motor, and then you can easily find out the torque through the number of revolutions. So I'm showing you this on an example. Let's say we have a so-called NEMA 17 stepper motor, which has a nominal current of 1.8 amperes, and you're having 1000 number of revolutions in your applications, and then you're going to the data sheet at the 1000, and then you're checking, do you have 24 or 48 volts? In this case, I have 48 volts, and which is the orange line. So if I would have now a current of 1.8 ampere, then the torque would be around 0.4 Newton meters. In this case, it's only 1 ampere instead of 1.8, so it's roughly 50% of the current, and that's why it's also roughly 50% of the torque, and that's why in this case we have 0.2 Newton meters in your motor, and that's how you can find out the torque which your motor has. If the gear is directly on the motor, then you can use this torque directly. If you have any other gearboxes in between, then you of course need to calculate the torque and speed you will have at the end at your gear which you want to calculate. The other case I'm explaining here is a direct current motor, so a so-called DC motor. DC motors, it's much more easier. You have a specific torque at a specific number of revolutions, so it's really easy. You put on your applications, and then you measure the number of revolutions at load. So when your application is running, and then with this number of revolutions, you just go into the data sheet, and then you can measure or find out really easy the torque on your gear. Again, an example here, we have this so-called motor here. we got the data sheet. We had measured 220 RPMs in the applications, and according to the data sheet, I have 0.25 Newton meters. And yeah, that's how easy you can get the torque you have at the gear with such a current motor. Again, if there's a gearbox afterwards, you need to calculate it down to the torque you have really on the gear at the end. But of course, now we have already find out, yeah, it works in my application. And yeah, now I want to do some test runs. And what we often see is we get 3 models in a bad shape from customers. So where the teeth is simplified, or there's no radius at the foot, and this is causing more noises and a much reduced lifetime. That's why I want to show you here the difference between a good shaped teeth and a bad shaped teeth. Because at 3D printing, I take the 3D model directly on the printer, and the 3D model should be shaped like the ideal version of the part. Yeah. So this means the involute tooth needs to be shaped and everything. The dimensions should be on the tolerance center. So for example, let's say you have an inner square with 10 millimeters and a tolerance of plus 0.2, then the 3D model should be on 10.1, so in the middle of the tolerance field. Because if the model is on 10, we cannot be inside of the tolerance field, because we're always having sometimes a bit smaller, sometimes a bit bigger, and if you put it on the in the center of the dimensions, then we can make it also with the tolerance. And yeah, another often question is about what clearance do I use when designing the gears. So any external tooling or teeth, like at such a gear or at such a gear, you can use the nominal size. You don't need to add any clearance. But if you have any internal tooling, so similar to the gear you have here, then you should have an additional gap of 0.1 millimeter added, so that the gear works afterwards. Which means in a diameter, the diameter should be 0.2 millimeter bigger, and then it should work without any rework. Yeah, how to get such a model? We have here a free configurator where you can configure such a gear directly, where you have the involute shape, you have an optimized tooth foot with a much better lifetime than with regular gears or regular CD programs made, but it's still compatible with any other involute gear. So yeah, I really recommend to use this configurator to make your gears or your 3D models of your gears, so that you can print them by yourself or check prices at igus, and to have a much better lifetime than with such regular or simplified gears. That's what we often see. And yeah, another important point is the shaft hub connection. So how do I connect the gear to the shaft so that the torque is also transmitted from the shaft through the gear? And for plastic gears in general, any form fit works really good, like a flattened shaft or inner square, what we have here, a bolt, key groove. A grub screw doesn't work so well. It's only really a small torque which you can transmit through a grub screw, or any other way how to have a form fit, of course. What's not so suited for plastic gears is, one moment, I need to check. Yeah, okay, we will answer the questions at the end. Yeah, what's not so suited for plastic gears is any other form than form fit, like connection by force or friction, like heat shrinking or press on a shaft. That's what not so well working on the gears. Again, we are answering the questions at the end, everything together. Okay. Yeah. So when do I have cost advantages with 3D printed gears? This is really easy to find out. You just upload your 3D model. I can show it to you. You can upload your 3D model at our online print service. You get immediately prices. Here, for example, it's €3.80, and the prices also changes over the quantity. And that's how you can easily find out if 3D printing is cheaper at my special gear here than regular machining. But yeah. And yeah, here's also another overview to help you a bit more when which manufacturing method is more suited than other methods. So basically, we can injection molding, we can do machining, we can do 3D printing, we can also do injection molding with 3D printed molds. And yeah, you see the different methods when each method is cheapest, based on different sizes of bearings. So 10mm bearings, 20, 30, 50, and 90mm bearings, and then the different quantity of the bearings from 1 to 10,000. And you see in general, if the part is very small, like a 10mm bearing in this case, 3D printing or laser sintering is the cheapest method, even up to 1,000 pieces or even up to 5,000 pieces. Because if I have such a small part, they're fitting like 5,000 pieces into the print room, which makes the part price below €1, which is much cheaper than the other methods. And if the part is getting bigger, less parts are fitting in the print room, the part gets more expensive, and then other methods are cheaper, like machining at small quantities, injection molding at high quantities, and sometimes also injection molding with 3D printing 3D printed tools in mid-range quantities. Of course, this is a bearing, so a regular or more simple part in this case. At gears are more complex to make, so there are more or higher tooling costs or more costs to set up the production. That's why at gears, the area where 3D printing is suited is much bigger compared to bearings. And that's what I also want to, I should open the presentation. That's what I also wanted to show again. So we're not only making gears by printing, we're also milling the gears, we're doing injection molding and injection molding with 3D printed gears. Don't hesitate to contact your igus contact or also me to find out what's the best method for your application. Yeah, and at the end, I want to show you some applications we have. Here, for example, there's a customer which had some gear issues in the water gun because the gear was broken, and otherwise he would have to replace the whole water gun. And yeah, we printed the gears, and he did also some lifetime tests, and it worked really well, even when the water gun is running, because yeah, you can maybe understand it. If the water gun is working, there's a high load because it's a high pressure when the water is thrown out. And even when the water gun is running, the pivoting mechanisms needs to drive with the printed gears. And even in these cases, it's no issue for the 3D printed gears. Another case we had here in Cologne. It was a tractor which we couldn't use anymore because one of the gears was broken. In order to start the motor, we measured the old gear and yeah, did a new drawing and printed it, and then it's running again. And another example we have, it's not a gear in this case, it's a chain wheel. And in this case, the customer also had some issues with noises. So this chain wheel is only guiding the chain in this case. And the customer did draw the chain wheel again and yeah, replaced it with a plastic gear printed by Iglidor i3, and the noises were reduced a lot here in this case. And as the last slide, I'm showing you the tools we have. I showed you already the gear configurator, where you can configure your special gear. We also have it for gear racks, for rollers, for sliding plates, for lead screw nuts, and for bearings, so that you don't need to have any CAD knowledge or that you need to pay for any CD software. You can configure your own special gear in this tool, download the step model and yeah, print it by yourself, or check online prices with the online configurator or online print service, where you upload the model directly. And of course, you can calculate the lifetime of such printed parts for bearings and gears. Yeah, thanks for your attention. And now we have time for your questions. We already got some questions. I saw it. Thanks a lot. So what tolerance is achieved with SLS process if you want to get a good fit on the shaft? What yeah. Okay, so very good question. So the tolerances we achieve at the laser sintering is plus minus 0.1 millimeters up to a size of 50 millimeters. And if it's more than 50 millimeters, it's plus minus 0.2%. That's what we can achieve without any rework. With rework, we can achieve, of course, better tolerances. And then, yeah, you need to decide if this is good enough for your applications. We found out that it is yeah, good enough for lots of application because I said already we printed like 40,000 gears last year by laser sintering, from yeah, lot size from 1 up to lot size 6,000. Yeah, and the fit on the shaft depends, of course, how you transform the torque, or what kind of mechanism you have on the inner diameter in order to transform the torque. So kannst dich mal wieder einloggen. So basically you can, if you have, for example, an inner square and your shaft is 10 by 10 millimeters, then you can do on the gear 10.1, and then you are good to go. You can also do it on 10, so that maybe it's a slightly smaller sometimes. If you press it on, then you also have a yeah, more dense fit. What's the wear considered for the estimated service life shown in the result? Okay, very good question. Regular at or normally at gears, wear is not such a big issue. It's more an issue about when does the teeth break. So usually you don't have so much wear compared to a bearing, where really wear is the main issue of the lifetime. At the gear, it's really the point on when breaks the gear. So this is the lifetime calculation. It calculates when does the gear break. Because usually if a gear works well, you don't have any sliding. It's more like rolling. Yeah, very good question. What type of grease to use with 3D printed gears? None, because lubrication is already inside. As I'm saying, at igus we're putting solid lubricants inside of the plastic, so there's no external lubrication needed. If you have any way, out of some reasons, lubrication in your system and you cannot avoid it, most lubrications work also, but please don't hesitate to contact me or your igus contact in order to check out the resistance of your oil against the printing material. Shaft top connection. Yeah, again, another question about small. How small can we make, or can we do small worms and small worm gears? So as I'm saying, our minimum wall thickness is about 0.7 millimeters. We can also go down to 0.5. And for worm gear drives especially, so in this case, where we had a higher lifetime than with a regular machined worm shaft. No, yeah, worm gear, sorry. The running partner, so the worm shaft was aluminum anodized. So if you have a higher load or a high load at the worm gear drive, then the worm shaft needs to be metallic. If you don't have such a high load, then both parts can be plastic. I think another question we got, can you tap a thread in this material? Yeah, you can machine it like any other plastic you've got. You can put a thread in it. We can also, if the thread is big enough, we can also print it directly in it, but you can also machine it, of course, afterwards. Another good question, what does the gear service lifetime calculation work on gears with smaller gears like 12 teeth? For the gear configurator and gear lifetime calculation works only so far from 17 teeth on, because below 17 teeth there's like an undercut necessary at the teeth. And that's why we don't have it so far in the lifetime calculation and in the configurator. But of course, it is possible. If you need to have such models or lifetime calculations to such gears, don't hesitate to contact me so that I answer them by mail. Yeah, I hope we answered all the questions we got. Thanks for all the questions and for the attention. I will also answer all the questions we got by mail afterwards. And yeah, don't hesitate to contact me if you have any more questions about 3D printing or gears or all other topics where wear and friction matters. Thanks again and having a nice day.